This is how to go through a revenue equation in the quadratics unit. So here we've got a situation of an artisan selling 120 garden ornaments per week at $4 per ornament, and they've discovered, or market research has told them or something like that, that if they decrease the price 50 cents they'll sell 20 more ornaments, and for every other 50-cent decrease in price they'll sell another 20 more ornaments. Or the flip side works as well. If they increase the price by 50 cents then they'll decrease the number of ornaments sold by 20. So we're asked to write an algebraic expression that links revenue and price and quantity together, turn that into an equation, and use that to find the price that yields the maximum revenue and what is the actual maximum revenue. You'll notice here the word maximum and the word maximum again. So let's just highlight each of those. Maximum, highlighted. Maximum, highlighted. As soon as you see those things, you think vertex. So here's how we kind of get started. We know that we need to have a let statement. The let statement is let x represent the number of price decreases. We're going to decrease it by 50 cents. Once or twice or 3 times or whatever. And we're governed by this overall expression, revenue equals price times quantity. So then we need to come up with a price statement and a quantity statement. It'll look like this. The price is the original price, $4, minus 50 cents times that number of decreases, x. And the quantity is 120 ornaments plus 20 more ornaments times however many price decreases there were. Combine those together, you can get a revenue statement, which is revenue is price times quantity. And that is a quadratic function expressed in factored form. We've seen that before there. So if we want to find the maximum, we need the vertex. To try and find the vertex from factored form, we start off by finding the x-intercepts by setting each bracket equal to 0. And then from that we'll be able to find the vertex. So here's what that starts to look like. The first bracket equals 0, 4 minus 0.50, x equals 0. Rearrange that, you find x equals 8. Solve it. Okay, and the quantity expression, the second bracket equals 0. Solve for x, you get x equals -6. If you look at this graph here, you don't necessarily need to do a graph of it, but it's useful to sort of see what was going on. You can see that the x-intercepts were -6 and 8, which is what we just calculated. That's the x-intercepts. We want to know the vertex because we're trying to find the maximum. And so we need to find the halfway between 8 and -6, which essentially means average those two values. So add them up and divide by 2 gives you 1. That's going to be the x-coordinate of the vertex. Sometimes we call that h. And then once we know that, we can sub that back into the full equation to find the y-coordinate. Right, we sub here. We take that 1 value, which was here, and we sub it into the original equation. X is now replaced by 1, there and there. Both places, there and there. And we can calculate that. 3.5 times 140 is 490. So the vertex is 1, 490. Here on the graph you can see that that is the case. So what does 1, 490 tell us? It means that the maximum revenue is 490 and it happens when x equals 1. That doesn't mean the price is 1. Remember, the price is an expression involving x. So to find the exact price, we need to substitute that x value of 1 in. So the maximum occurs when x equals 1. Price then is 4 minus 0.50 times 1, which is 3.50. So the maximum revenue is $490, and it happens when the price is $3.50.